for the introduction. Hello, everyone. First, I would like to once again thank the organizers for putting up such a nice school, for giving me the opportunity to teach quantum thermal last week, and also for allowing me to present a different work in the workshop. So, as announced, today I'm going to talk about privacy in distributed quantum sensing. This is a joint work done in collaboration with Jonathan Borbrask, Benjamin Larsen, Ulrik Lund Andersen, which is sitting just over there. All of us from Technical University of Denmark, Masahiro Takeoka from Keio University in Tokyo, and our collaborators from Sorbonne University, Anton, Sean, and Damian. The way that I divided this presentation is mainly in three parts. First, I'll start with a very general and hard question, motivate you with a very simple example, and state the problem that I would like to discuss. Then I will roughly talk about this notion of privacy. Then I will finally present our results and conclude this presentation with an outlook and some open problems. So let me start then with a very general question that kind of captures what I would like to discuss today, defines this field. And as I said, this is in principle a very general and hard question, namely, how can we ensure that the information processed in a quantum network is secure from malicious parties? And as I said, this is a very general question. In principle, we can address it from very different frameworks, but the way that I'm going to do in the next slides is to find a simple instance of this problem that you can translate it into a multi-parameter estimation with certain constraints, cryptography constraints. And actually, this is not new. The first time that people combine metrology and cryptography, it's dated more than 20 years ago. But in the last years, there was a resurgence in the literature of people adding those privacy constraints that I will explain. There was first a framework to do this in discrete variable systems. First, experiments starts to appear. How you characterize this notion of privacy, like what are the necessary and sufficient conditions, and how you can construct private states, also emerge. But then there's a bit of the caveat here that I will mention along my presentation, that mainly of those results, they basically hold for discrete variable systems. But before talk about those results, I would like to start by presenting the question that I would like to address today with a very simple textbook example. Yes, there are many more as well. And so let's assume that we have some parties and there's a source. And the idea here is that parties will request a state for the source prepares this state and distributes to the parties. So our goal is that each party will encode some information in the network. This information will be collectively processed by the parties and to output a given target function. And the constraint that I will add is that the information that it was encoded by one of the parties is private with respect to other members of the network. To make this problem more simple, we can think in the paradigmatic case where we would like to estimate the average phase. So, for instance, suppose that the parties ask the source to prepare a JZ state, the source prepares and distributes this state, then locally each party will encode some phase. This can be done by a general CPTP map. Here, for the sake of simplicity, I will assume just a local encoding, such that now the encoded state carries this information that it was encoded in the network. And since we would like to estimate the average phase, parties perform some local measurement that we could agree beforehand. With this local measurement, then you have access to some conditional probability. And by repeating this many times, we have some data and we can process this data with statistical methods. So the question that I would like to pose is, do outcomes here reveal only the average phase and nothing else? Well, in this case, the answer is pretty simple. For instance, if we look at the encoded state here, our state is proportional to a quantity that it's proportional to the average phase. So what we could do here is just redefine this problem as a single parameter estimation. So in other words, if we perform those measurements, basically we are able to only estimate the average phase and nothing else. Not any other combinations of phases, including also the individual phases. So for this case, we say that JZ states are private states. In fact, they are called complete private because for this state, we can only access the average phase. But notice that up to this point, this is a property of the encoded state, right? Because let's say that the source, instead of preparing JZ states, it prepares copies of plus states. Well, if we repeat precisely the same encoding and the same type of measurement, what we will learn is that copies of this plus state allow us to learn all possible parameters, because now the encoded state also contains information about pairwise phase, individual phases, and so on. So in this case, we will say that this state is not private. As I said, we know what are the conditions that we need and how to construct those private states, but then the natural question is, what happens for continuous variable systems? Suppose now that my resource is a Gaussian state. Is it the case that those necessary and sufficient conditions can also be extended? Well, just as a motivating example, and naive thing that we could do here is simply replace, for instance, our initial JZ state by some sort of Gaussian JZ state. Here, since this state has a complicated dependence, and since we are at quantum-weighted dunes, I will represent this state by just a Gaussian dune. So if we repeat precisely the same protocol, what we will learn is that differently from the discrete variable JZ state, the Gaussian version of this state will not be private. Actually, we can again learn everything, all the individual parameters, and so on and so forth. So then, this leads us to ask the following question of this presentation, which is, can Gaussian networks achieve private sensing with experimentally feasible resources? Well, here I'm restricting to Gaussian states because it's not so hard to think that if we allow an arbitrary state, I could construct a very non-Gaussian state and achieve this, achieve private sensing. Also, I'm putting constraint here on the fact that I want to have something which is experimentally feasible, because if I don't constrain the energy, of course, that if I take my squeezing parameter that I will mention later on and send to infinity, then we could, in principle, trivialize this question. So basically, this is the problem that I would like to discuss today. So to do that, we have to talk about this notion of privacy that so far I just roughly define. And as I told you, the way that we are looking at this problem is as if it is a multi-parameter estimation with certain constraints. And the question that we could ask in this slide is, which parameter directions are learnable from a given encoded state? Well, how well I can estimate a given combination of parameters is given by this information theoretic quantity called quantum Fisher information matrix, more precisely its eigenvalues. So basically, the eigenvalues of this quantity will give us a bound on how well we can estimate a given combination. And just to recapitulate, what we are looking here is that we will have a network. So in this network, we encode parameters. If I'm assuming that the network has size m, we'll have theta 1 up to theta m parameters. And basically, those thetas will recombine such that now we'll have combinations or directions. And our idea is to compute a target function which is linear and can be written as a dot product like this. I don't need to focus on a specific function. For this talk, I will look at the average phase estimation. So this means that this direction that I'm interested is something proportional to 1, right? Because if I take this dot product, I will have something like theta 1 plus theta m. Great. So since the eigenvalues of my quantum Fisher information matrix give us a bound on how well we can estimate possible combinations. My definition of privacy will also encode this property. And for this talk, I will present two operational levels of privacy, strong or complete privacy, which is precisely the case of the JZ state where you can only estimate the average phase and nothing else. But as I will argue here, and a spoiler of my presentation, fortunately or unfortunately, continuous variable systems cannot be made complete private. So we will also look at this weak version that we call the weak privacy, which we allow ourselves to have some leakage, meaning that some combinations of phases can be leaked, but the individual phases are still protected. And even that some members of the network has access to these other combinations, they cannot reconstruct the individual phases. So it is like solving a linear system and you have less equation than variables here. So the best thing that you can do is an educated guess. Well, the way that we define privacy, maybe this is not the simpler way to see at first glance, but the idea is, imagine that we have some vector u. This is just a combination, and we define also the directional derivative of our encoded state with respect to this vector u here. So we say that a vector u is unobservable at theta if its directional derivative vanishes. So basically what this definition is telling us is that if we take our encoded state, if we take the parameters and shift linearly around this direction, we will not see anything on the statistics of our experiment. So basically this is blind towards linear shifts along this direction. And then we say that a component theta j is private at theta if there exists an unobservable direction u with non-zero component. And basically here the idea is that even if you have this shift, which is controlled by the fact that this uj is different from 0, you are still blind in the statistics of your experiment. Well, I must say that there is a chain of equivalence between this definition with properties of the quantum Fisher information matrix that I'm not presenting. But this definition gives us a clear way of identifying private components. So basically we say that a component theta j is private if there exists an unobservable direction which lies in the kernel of this quantum Fisher information matrix. And the component here is non-zero. So basically what I'm telling you is the following. You have your encoded state, you compute its quantum Fisher information matrix, you diagonalize this quantity, and then you have some eigenvalues. These eigenvalues will give you some bound on how well you can estimate a given parameter, but then if you are lucky enough, one of these eigenvalues is 0, which implies that the corresponding eigenvector, which is precisely a direction, cannot be estimated with finite precision. So very simple. I will also allow myself to process my encoded state, as we will see. So since this definition only gives us a binary characterization whether a component is private or not, I will also quantify privacy by simply taking my quantum Fisher information matrix, kind that projecting along the direction that I would like to estimate, and then normalize by the total information. So basically this gives us a measure which is between 0 and 1. So if it is 0, it means that the direction that we wanted to estimate, such as the average phase, lies in the kernel of Q, so we don't have any information about it and we cannot estimate it. If it is 1, this is very nice because it is just like in the case of JZ state. So in other words, this quantum Fisher information matrix here is rank 1, and the only eigenvector there which is not in the kernel is this eigenvector here. And this quantity can also be between 0 and 1. And when it is 0 and 1, I have to check if at least I can achieve privacy at the level of components. Good. Okay, so given the fact now that I have this nice characterization of privacy, so now it's time to look at our setup and also to come back to this question that I start. And basically, again, rephrasing this question, now we can say, what can't Gaussian resources plus linear optics reveal about theta? So basically what I'm going to do now is that I'm going to consider some Gaussian state. I will allow myself to pre-process, meaning that I will allow myself to perform any linear optics operation and then try to infer which components is private or not. So the natural question is, okay, if a continuous version of a JZ state is not good for privacy, which state it's a nice one? Well, this is a bit of hand wave argument, but if we think about metrology, Gaussian metrology with homodynamic measurement, single parameter estimation, we know what is the optimal probe, a single mode exquisite state. Here we want to do multi-parameter estimation, encodes this idea of privacy. A nice state to have it is a two-mode exquisite state. Again, because of the conference as a homage, I will depict the two-mode exquisite state by this Gaussian dune here. So the idea then, as I was saying, so we have as a resource a two-mode exquisite state, and then important point that I'm not mentioning here is that whether we trust on the source or not, because it might be that the source is cheating and then instead of preparing a two-mode exquisite state, prepare another state. So up to this point, I will assume that we trust on the source. If we don't trust, we need a verification protocol. But we also have a verification protocol that I will mention in my last slide, but here I will assume that everything is trust. However, I will allow myself to prepare states which are not perfect, meaning that there will be some losses. And these losses will be modeled by assuming that here each mode undergoes a bin splitter with vacuum in one of its parts, and this bin splitter has transmissivity eta 1. So if eta is equal to 1, you don't have loss, but then if eta is not 1, then you have some loss quantified by this transmissivity. And then, as I said, we allow ourselves to apply arbitrary linear optics. Here, in principle, we could think about displacing to try to counter this loss, or displacing before, and so on. And the idea of doing this is because we really want a general protocol. The next question is, okay, nice, you have a resource, but you also want to look at this into a network, right? So you have to build this network. The question is how we do this. And the way that we will do this is following this protocol, which was proposed in this very beautiful paper here, also from Ehrlich, where they were looking at distributed quantum sensing, where now to construct this network, what we do is the following. We have our two modes here. We append bin splitters with vacuum in one of its parts, and we mix them in this equally, in this 50-50 bin splitter. So what happens now is that I will double the number of modes, and this is a symmetric state, a symmetric entangled state. So this is a network of 4 parties, but if I desire to extend the size of this network, I can proceed with the same reasoning. I can append bin splitters, and again, mix them 50-50 with vacuum. Once I do this, once we agree on a specific size of network, parties will perform some phase shift. And just to emphasize that those phase shifts here are local. After doing this, we perform some homodynamic measurement, then we have a conditional probability, and then repeating this, we have some data to process this experiment. Well, why this is interesting? The first reason is that since everything is Gaussian, I can treat this problem completely analytically. It's fully analytical. And when I say fully analytical, it means that the relevant quantities for me, such as the quantum Fisher information matrix or the eigenvalues, I can analytically compute for an arbitrary size of a network. And second, it's also experimentally friendly. And right now, we also have an experiment in progress in DTU. And up to now, what we did was to create a network of 4 parties. We already have some data, and we are analyzing the privacy up to this point right now. And I will mention this in a bit as well. So basically, we have this very nice experiment in progress. This is everything analytical. So the question that boils down is, what is the privacy of this network, right? Because it might be that okay, this construction is very nice, but this resource doesn't give us what we want. And let's look at the simplest case scenario, because when we generalize, things doesn't change too much, only the expressions which get a bit more complicated. So let's just assume that we have this two-mode squeezed state, and we are sending this two-mode squeezed state into this beam splitter network and encoding phases. So then the question is what we can learn about this network. As I said, we have an analytical expression for the quantum Fisher information matrix. We can diagonalize it, get its spectrum, and its spectrum is basically given by this quantity here. So we are lucky enough that one of the eigenvalues is 0. So this means that there exists an unobservable direction. We have this big chunk of the generated eigenvalues, and there's this other unique eigenvalue here. When we take a closer look at those eigenvalues, we learn that the one which gives us 0 is associated to this eigenvector. This is the unobservable direction. And the nice thing here is that since all the components are non-zero, so this means that each theta j is individually private. Well, if now I take a look at these other two eigenvalues, it's not so hard to see that they will grow with different rates. If I write them as a function of the number of mean photons hitting in this phase shifter, what we learn is that, well, this second eigenvalue here, which is associated to the alternating phase, scales linearly with the number of mean photons hitting the phase shift. Whereas the eigenvalue that we are interested, the one corresponding to the average phase, scales quadratically with the mean number of photons. So this means that we can estimate this much better than the one that we dislike. Well, as you can see, this state doesn't give us complete privacy, because in order to give complete privacy, we would have this quantum Fisher information matrix to be rank 1, and it's not. So then we could ask what levels of privacy, according to this measure, we can achieve. And since everything is analytical, we can plug into the equation, and then we get this quantity here. So it is basically 1 minus a positive quantity. A positive quantity which increases with the size of the network, m, which kind of makes sense that we lose privacy by extending the network, because basically every time that I append a beam splitter, I'm unlocking 2 other new directions, right? And this quantity also, what is interesting is that it decays with the amount of squeezing. So meaning that, yes, if we have infinite powers, if this squeezing goes to infinity, in principle, this quantity would go to 1. But let's take a closer look at this, at those results when we look at a specific size of network. Let's take a look at the case that Benjamin is looking at the experiment, the case where we have 4 modes. And now I will allow myself to have, as I said, arbitrary linear optics operation. So for instance, let's say that we displace the modes after producing it just to counter with this loss that we will eventually have. So when we do this, what happens is given in those plots. So let me go through them very careful. So basically, let's look at the case in which I don't displace the mode. If I don't displace the mode, that equation gives me something like this. And basically, this is the optimal scenario, meaning that if I now start displacing to counter the loss that I will add, then I break privacy. So basically, by displacing, I remove the kernel of the quantum Fisher information matrix. Well, if I have some loss, what will happen is that the privacy will decrease, but it doesn't decrease because we are leaking information or that we are removing the kernel of this quantum Fisher information matrix, but also because this measure is tied to how much I can sense this quantity. And of course, that if I have loss, I will lose in sensitivity. But what we proved, which is not here, unfortunately, is that even if you had this loss, which is just this Gaussian channel here, you can still have privacy, weak privacy. Well, and then what our results also give us is a way of constructing optimal regimes under loss and displacement, in the sense that suppose that, well, you have a very lossy let's say, environment and you wanted to displace to counter this loss, then we could ask, how much are you sense by sacrificing a bit of loss? So our results also allow us to look at these optimal parameter regimes. And then, of course, that the question that we could ask is what happens if we change our resource, if we don't look at a two-mode exquisite state, but another Gaussian state. So basically, our results also cover this. We also provide analytical ways of assessing the privacy for arbitrarily Gaussian states. And so here I just put 3 examples where of states that we can produce in the lab. A single mode exquisite state. So basically here I'm feeding the network with product states. So of course that this is not private, and this is actually achieves the lowest level of privacy. A cluster state of 4 modes, which also doesn't behave well with the amount of squeezing. And even if you optimize over the coupling, and then, and finally our 2-mode exquisite state here. So it seems that the 2-mode exquisite state is quite nice for this task. And now, just to finish this talk, 1 week after we put this paper on archive, those colleagues from Finland also look at precisely the same circuit as us, but instead of using a 2-mode exquisite state, they construct a Gaussian state tailored for this protocol. And what they show, even if you tailor this state, is that you cannot achieve complete privacy. And yes, you cannot achieve complete privacy, and the cost for producing this state is also a bit complex. So finally, let me finish this talk by saying that, well, I discussed a continuous variable protocol for privacy in continuous variable system. What I didn't talk about, but we have, and it is really nice, is the certification protocol, which also allow us to not only certify 2-mode exquisite states, but many other family of Gaussian states. And then I would like to leave with 2 questions. The first one is whether we can achieve strong privacy in continuous variable system. Unfortunately, 2 weeks ago, I was in this workshop in France, and apparently I heard from Matteo that they already proved this first point. So the second question is, okay, if we cannot achieve strong privacy in continuous variable system, what is the best thing that we can do? Like, do we have better Gaussian protocols? And with this, I would like to thank again the organizers for the very nice event. I look forward for the nice talk, and thank you very much for your attention.
Okay, questions for Alex? Yes.
Thank you, Ale, for the talk. My question is related to the certification protocol, because you did the theory for this specific state, but what are the types of fidelities that you observe in the experiment? Maybe this is more an experimental question. I'm wondering, because for the GHZ state, it's very hard to get very high fidelity, but whether for the Gaussian states, one can get very close.
Yeah. So what I can tell you is that when we compared with the data that we have, we didn't get good fidelities. So then the question is, why is this? What is the source of, let's say, noise, or which parts which is making this connection hard? Because in principle, we could get, right, with them. Yeah.
Other questions?
Sorry.
Oh. A hard question comes in.
No. Very nice talk. Just a general idea. What if you kind of like randomize the setup, the construction of the Gaussian states by doing a random rewiring of the modes? Then kind of like the individual parties don't know which mode they belong to. The sum is still invariant under permutations, and there's the hope that if you average over these permutations, you might get more zero eigenvalues.
Yes, this is a very good question. We didn't think about it. And one of the reasons why we didn't think about it was because there was this race to prove that Gaussian states couldn't achieve this complete privacy. And then once we found this, the idea was, okay, what is the best protocol? So basically, this could be a way out, yes?
Yes,
Exactly.
In
yes.
fact, when you, I mean, if
it's like think about like variation algorithms, and if you have deep circuits and averaging, or like do the science of stuff, you get like partial derivatives that are like exponentially close to zero. So it's basically what
Yes.
you're wanting for. So it makes a lot of sense what I'm saying. Other questions? Okay, we can thank Alex again.
Thank you.